Hello Coach Reza and everybody watching this video. Uh, let's understand what we have to do in assignment 2 and how we're going to do it. So going to the question, we are supposed to do predictive modeling, and we have some data related to weather conditions. And here's a brief about the data. We have 4 independent variables and 1 dependent variable, and this is the ask: Python code, PowerPoint, and a YouTube video. So first let's get into the data. So we have 96454 records, which is a good amount of data. Not bad, good. And as the documentation said, we have 4 independent variables and 1 dependent variable. So temperature has to depend on all of these, and basically there has to be some correlation between each of these features with temperature. Okay, so we'll get into how we will analyze that, but for now this is a summary of what we have. And moving on, let's first understand what linear regression is. So linear regression is a predictive analysis model which uses a straight line to best describe the relationship between a dependent variable y and one or more independent variables x or x, z, a, b, c. So this is how the model will look like. It's supposed to be a straight line, and we have the points here and there. Suppose one here, one here, one here, one here, and we will use this line for future predictions based on the dots that we have, or the data points that we have. So how we describe a line is y equal to mx plus c, where m is the slope and c is the y-intercept. So this is c, and here we have the example. So it's 2 plus 5x. So 2 is c, the y-intercept, where the line intersects the y-axis, and 5, that's the slope for this line. Since it's a positive 5, we see the line going this way upwards, but if it was a negative 5, it would have been this way down here. So in the linear regression model, we will come to know the y-intercept and the coefficients for each of the variables, each of the features or the dependent variables, and beta 0, as shown here, would be the y-intercept, basically where the line would intersect the y-axis, and beta 1, beta 2, beta 3, beta 4 onwards would be the coefficients, or basically the slope for each line and its relationship with the dependent variable y. So yeah, so we will go into how we're going to do the bivariate linear regression. So as we know, we have 4 dependent variables and 1 independent variable. So that makes the linear regression model a bivariate linear regression model, basically, since there are more than 1 variables. So going ahead, we'll just see how we are supposed to make a linear regression model and predict. So this is the place where we import the required packages, and mostly, like every other machine learning algorithm or code, we always need pandas, numpy, we might need to plot something, so it's good to have matplotlib.pyplot in here, and it's good to have seaborn too. So this is the step where we read the data and put it into a data frame. Then we just print out the top 5 rows of the data just to check whether it's the right data that we have imported. Then we have the data df.describe, data frame.describe. This gives the key statistics for each of the columns. So I have jotted down the key statistics here. So first of all, the count means that we have so many records, and for the humidity, if we see, we have mean, that is 0.734, standard deviation is 0.195, which is not a lot. That means the data is not spread out from the mean, it's closer to the mean. All the points are scattered towards near the mean. We have the median 0.78. This is also the 50 percentile mark, which falls between the quartiles. This is the lower quartile, that's 0.6, and the upper quartile is 0.89. This should be 0.89. So basically we can imagine that this data, since it doesn't have a lot of spread, and also the spread from the min, that's 0, to the first quartile, to the median, and the second quartile, and the maximum, there's not a lot of variation between these numbers. So this means that since the spread is small too, the data may not be skewed. Similarly, for wind speed, we have mean 10.18, standard deviation is larger than this, median is 9.96, the first quartile is 5.82, and the second quartile is 14.1, but the maximum is 63.85. That means from the second quartile, that is the 75th percentile, after that we have a lot of or maybe we have a few data points, but some of them are scattered far away from the 75th percentile. So that means we might imagine that this data could be right skewed. Maybe there's even just 1 or 2 points that's so much far away from the second quartile, but this makes me feel that this data could be right skewed. Similarly, for visibility, we have the mean, standard deviation 4.192. This is also not much. 4.192 is okay. Median, and these are the quartiles, and range is only till 16, so we can see 0 to 8.3 to 10 to 14.81 to 16.1 is like evenly distributed. It's nothing very apparent to the eye. So this may not be completely skewed or largely skewed. Maybe there's a little skew, but it's okay. And also the data is not a lot of spread from the mean. So these are some key insights that we get from the describe function. Now we get to the main part of the linear regression model. So we are splitting our data into the dependent variable and the independent variable and the set of dependent variables. So we have 4 dependent variables, and so we will put the dependent variables in X, it's going to be a data frame, and from this data frame we're going to drop temperature and make it a numpy array and put it into x. And similarly we will only have the dependent variable temperature in another variable called y, and it's going to be a numpy array too. Now we are going to further split x into train and test and y into train and test using train test split function from scikit-learn model selection library. And we have specified here that the test size is going to be 0.2 and the train size is going to be 0.8. That means 80% of x is going to be used to train the model, and 2% is going to be used to test it. And similarly 80% of y is going to be used to train the model, and 20% of y is going to be used for testing. Random state is again it's an optional parameter, but if everybody if two people are doing the same algorithm and they want the same results, they would want to have the random state equal. Coming to the next part, so as we know, all the machine learning algorithms, even pandas and numpy, would work better if the numbers were smaller. Like it should not be like I mean it will work even with large numbers, but if the spread is massive, like the min is something like 10 and the max is like 10 million, so multiplying, dividing, adding, subtracting between big numbers is always going to be a problem, since storing big numbers in the computer in the backend is also going to take more space and more computation time. So it's better that we scale these numbers down. So that's what the standard scaler is going to do. We downscale the values, and we apply the scaling to x train and x test. So the dependent variables are scaled now. Then we go on with linear regression, and this is how we're going to do it. We import the linear regression model from scikit-learn linear model. Then we have we are going to use this later. We import another package called metrics, and from sklearn obviously, and we will be using this in the coming 5 minutes or so. And this is where we create a linear regression object. So our object is LR, and when we say n jobs equal to -1, we just say this because we want our computer to compute with all its cores, so yeah, so that the computation is quicker. Again, it's an optional parameter. It's not a mandate to have this, but it's good if you just have this one task running in your system and you want your system to run it with all its cores. You would want to use this. Then we have so this is where we fit the model. So this is where we are actually using the train data for the machine to understand what's going on with the data. So we pass the xtrain 2 because we transformed it with scaling, and ytrain because we want y to be as it is, since it's the dependent variable. So this is where the machine understands the box of rules behind how y is dependent on x. So now, since we have we've done lr.fit, this means now our LR object, or linear regression object, has the box of rules. It's understood what's going on in the background between x and y, how y is related on x. Now that we have it, we can use it to predict what's going to be x test 2. Yeah, so again we have scaled it. So I'm gonna put it into a variable called prediction, and so now we have the predicted values for x test 2, and we're gonna go ahead and print all these, the coefficients. So again, as I told you, the coefficients are nothing but the slopes for the lines. So these are the coefficients. So our linear regression model is something like this. Temperature is the independent variable, or maybe the y for us, y, and it depends on all of these variables, and this is the y-intercept as shown as the result of the function, and these are our slopes for each of these lines. So as we can see, since this is way closer to 0, or actually all of these are really close to 0 except humidity, so you can expect wind speed, visibility, and pressure to be lines that are almost parallel to the x-axis. That means it's not a slope, it doesn't have good correlation. It's like, it's a flat line, so you can't really predict that it's because of this or this that the dependent variable is here or here. Okay, so that's what we did. We printed the coefficients table, and we saw how these coefficients matter, what these are actually. Then we will come to check how good our model is, and we check it with the phi test. We check the r square score. So for us, the r squared is something like 0.45, and the adjusted r square is 0.452. So this doesn't appear to be a very good linear regression model. In fact, it's not good at all, since we have a lot of error. Mean absolute error is an error matrix. Oh, by the way, this is where we use the metrics package that we had imported over here, and we go ahead and we will so the metrics package, it offers you with all these functions to directly check the r square code to get the mean absolute error, the mean squared error, the mean squared error. Okay, yeah, this one is the root mean square error, so we have it in a square root, and we come to see that the mean absolute error is 5.68. It's not a good model. This value should be closer to 0 for a good model. Also, r square and adjusted r square should be between it should be between 0 and 1. So 0.45 is like even lesser than 0.5, so that makes this not a very good model. And mean absolute error is should be close to 0, but it's like 5.68. Mean square error is really bad. It's 49.69, and root mean squared error is 7.05. So overall, our model is not really good. but we'll come to the reasons for that. And this is a forecast table, so in this we get to see how well our model is actually performing, or in our case how bad it is actually. So the actual for these are the data sets. These are rows from the data set. So we have it should have actually been 22.2 in this case, but our model has said it should be 11.3. So that's a big difference. Then again, each of these readings have almost a difference of 5 units. There are some exceptions though, but generally our model is not performing very good. So what could be the reason? As we saw, R square score, this signifies how much of the data is our model really doing justice to. So when I say that, means how much percentage of the entire data does the model actually comprehend, and how much is it able to justify, or how well can it actually predict based on the data that we have. And that's like only 45% of the entire data. So that's why our model is not doing well. I mean, it's not the reason, but it's a symptom. It's like, it's R square basically tells you that. But some of the reasons that we have here are one of the main reasons is that we have features. These 3 features, these are not actually good features. They are not explaining a lot about the temperature. So the temperature doesn't really depend on these 3 features. It doesn't have good correlation at all. So we should go ahead with linear regression only if we see that our dependent variable has a good amount of, or a fair amount of correlation with the dependent variables, with the independent variables. So that's another reason. But if this model had to be improved, we might want to remove these 3 columns, and then only based on humidity, if we get the model, it would perform better. And also okay, yeah, that's all. Anyway, I hope you have understood everything, and so that's about linear regression and assignment number 2. Thank you very much for watching, and have a great day ahead.